Water crashes through a dam, a refrigerator hums in your kitchen, gasoline explodes inside an engine, and hydrogen fuses in the sun's core. Physics sees all of these as the same event, energy changing form. In this video, we build the single most powerful bookkeeping rule in science, conservation of energy, and the framework of system and surroundings that turns it into a working equation. No energy is ever created or destroyed, it only transforms. Start with falling water. Held behind a dam, water stores gravitational potential energy. Release it, and that stored energy becomes kinetic energy, the energy of moving matter. The rushing water spins a turbine, and the turbine drives an alternator, doing work that generates electrical energy. Power lines then carry that electrical energy to consumers, ready to transform again inside every device you plug in. Notice the structure of this story. Nothing was created at any step. One form of energy was handed off to the next, from height to motion to work to electricity. Every stage is a transformation, and the chain is only as interesting as the forms it connects. Now run the chain in a full loop. A refrigerator takes in electrical energy and uses it to compress a gas into a liquid. During compression, some of the internal energy of the gas transfers into the random motion of molecules in the room outside. That is why the coils on the back feel warm. The liquid then flows from the high pressure region to a low pressure region where it evaporates. During evaporation, the liquid absorbs energy from the random motion of molecules inside the refrigerator, which is exactly what cools your food. Finally, the gas returns to the compressor and the cycle repeats. Electrical energy in, internal energy shuffled from the inside of the box to the outside, a transformation engine running in your kitchen. Human beings run the same kind of process. Your body takes the stored chemical energy of food and transforms it into the forms needed to maintain organs, tissues, and cells. And you can do work on your surroundings, pedal a bicycle hard, and you transfer energy outward, ultimately increasing the random motion of air molecules around you. Every bit of that effort traces back to catabolic chemical energy released from food. Metabolism is not a metaphor for an engine. It is an engine running on chemistry instead of gasoline. The gasoline engine makes that comparison literal. Burning gasoline converts chemical energy, energy stored in the molecular bonds of the fuel, into the coherent, ordered motion of the molecules in a piston. That word matters, coherent. The molecules of the piston move together in one direction, rather than jiggling randomly. Gearing then carries that ordered motion to the wheels, and the tire road friction converts it into the kinetic energy of the whole car. Chemical bonds break in a cylinder, and a 2-ton machine moves down the road. 2 more transformations round out the picture. Stretch or compress a spring, and you store elastic potential energy, ready to be released later as kinetic energy. And the vision itself begins with an energy handoff. Stored atomic energy is released as electromagnetic radiation, that is, light. That light travels to your eye, excites photoreceptors, and releases chemical energy that your nervous system turns into sight. Even reading this screen is a chain of energy transformations, from atom to photon to chemistry. The same accounting holds at nuclear scales. Take a proton and fuse it with deuterium, a hydrogen atom whose nucleus contains a neutron and a proton. The fusion produces helium-3, whose nucleus holds 2 protons and 1 neutron, plus radiant energy in the form of photons. Here is the key comparison. The combined internal energy of the separate proton and the deuterium is greater than the internal energy of the helium-3 they become. Energy did not disappear in the reaction. The difference in internal energy is the energy carried away by the photons as light. The books still balance. Nuclear physics obeys the same ledger as falling water. Step back and list what we have seen. kinetic energy, gravitational energy, thermal energy, elastic energy, electrical energy, chemical energy, electromagnetic energy, nuclear energy, and the list goes on. Across every process, one universal pattern held. Forms changed, but the total never did. In every single transformation, the total energy is conserved. That regularity is not a coincidence to admire. It is a law we can compute with, and computing with it requires making it precise. Here is how we make it precise. Characterize any physical process by two states, an initial state and a final state, with the energy transformations happening between them. Label the different forms of energy E sub j, where the index j runs from 1 to n and names the form. Kinetic, gravitational, chemical, and so on. During the process, each form may change. Define the change in form j as delta E sub j, the final value of that form minus its initial value. Notice what this definition commits us to. We are not measuring how much energy something contains in some absolute sense. We are tracking how much each form changes between the initial state and the final state. Conservation of energy is now one clean statement. The sum of all the changes is zero. Delta E1 plus delta E2 and so on through delta E sub n. Add every one of them, and the total is exactly zero. In compact notation, the sum over j from 1 to n of delta E sub j equals 0. Read it as bookkeeping. Whatever one form of energy loses, other forms must gain, change for change. So the ledger closes at 0 every time. For falling water, the negative change in gravitational energy is balanced by a positive change in kinetic energy. The equation is the story we have been telling all along. Two important points follow from writing it this way. First, we care primarily about changes in energy, so the physics we develop will be relations describing how each form changes, not formulas for absolute totals. Second, the sum only closes if we account for every way energy can change. Miss a channel, and the books will not balance. That second point sets our strategy for the chapters ahead. We start with processes where atoms move coherently and ignore energy leaking into random atomic motion. In other words, we ignore friction at first, then we treat friction between rigid bodies, and later, in the first law of thermodynamics, we handle energy flowing into and out of random motion directly. Energy is always conserved across the whole universe, but tracking the whole universe is hopeless. Instead, we restrict attention to a chosen set of objects and call it our system. Everything else, the rest of the universe, is the surroundings. Picture three nested regions, an inner region, the system, the boundary enclosing it, and outside the boundary, the surroundings. Every energy analysis in this course begins with this move. Draw the boundary, declare what is inside, and treat everything else as outside. The choice is ours. The physics respects any boundary we draw. How the system talks to its surroundings defines three cases. Recall from Newton's laws that an object is isolated when there are no physical interactions between it and its surroundings. By Newton's first law, an isolated object undergoes uniform motion. The same idea applies here. An isolated system has no physical interactions with its surroundings at all. No energy crosses the boundary, and no matter does either. An open system is the opposite extreme. Both energy and matter can enter or leave. A closed system sits between. Energy can be transferred to or from the surroundings, but matter cannot. For this discussion, we work with closed systems, and the conservation gives the crucial consequence. Any energy leaving the system must cross the boundary and appear in the surroundings. Now state the key principle. When a system and its surroundings undergo a transition from an initial state to a final state, the total change in energy is zero. As an equation, delta E equals delta E subsystem plus delta E subsurroundings, and that sum equals zero. This is conservation of energy, and it is our operating definition of energy. We will sometimes call it the energy principle. Using it always follows the same two moves. First, identify the system and the surroundings, then quantify every energy change in each. One special case matters immediately. When the surroundings undergo no energy change, the equation collapses to delta E subsystem equals 0. The energy of a closed system is constant. That pair, the full principle and its special case, drives everything we do from here. The principle also tells us what a failure would mean. Suppose we add up every known energy change in a system and its surroundings and the total is not 0. Then either one of our energy expressions is wrong or a form of energy exists that we have not yet discovered. Hunting the missing energy is how new physics gets found. A live example. Cosmologists observe that the expansion of the universe appears to be accelerating. The leading account attributes this to dark energy, an energy residing in space itself, whose source is not clearly known. One of the most exciting open problems in cosmology today is, at bottom, an energy ledger that refuses to balance. Here is the complete framework. Energy comes in many forms, and every physical process, from falling water to fusing nuclei, is a transformation among them. Conservation says the changes always sum to 0. To use it, divide the universe into system, boundary, and surroundings. And for a closed system, write. The change in the system's energy plus the change in the surroundings' energy equals 0. Next, we make the first entry in that ledger concrete, the energy of motion itself, kinetic energy. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.